Hi, I am Varun Joshi and welcome to day 27 of our Certified Kubernetes Administrator 2025 course. In our previous lesson, we explored ephemeral storage types like mtdir and downward API, which are useful for short-lived container scoped data. But in real world, most applications need long-term durable storage capacity for stateful workloads like databases and content management systems. This is where persistent storage comes into play. Before I start this lecture, I have a request. If you are finding my content useful, then do like my videos, subscribe to my channel, and drop a comment. Even if it is just a hi or a thank you note, it does more than you know for me. So let's get going with the lecture. Persistent storage. What is persistent storage? So anything that prevails irrespective of the lifetime of the pod is persistent storage. For example, if I have connected a USB drive to my laptop, and if my laptop crashes, God forbids that happens, the data in my USB drive will still survive. Similarly, if I have a pod and I attach a volume to that pod from an external storage system, then even if my pod dies, that volume, that storage will still exist. So let's now discuss how persistent storage evolved in Kubernetes. I want to go to day 25, where we discussed that Kubernetes has a core and then there are things that are not part of the Kubernetes core. The core of the Kubernetes is container orchestration. Anything else, like how the underlying networking is handled, how the storage is handled, or how the containers are created, removed, these are not part of Kubernetes core. There are separate plugins, add-ons, and third-party extensions which can be used to enhance the capabilities of Kubernetes core. But there are things that are separate. In today's lecture, we'll be discussing storage, which is a separate part and is governed by CSI. So persistent storage. So there are two ways via which you can have persistent storage introduced into your cluster. First is the entry drivers and the second is CSI backed. Entry drivers are now deprecated. Historically, storage drivers were embedded in the Kubernetes core. So if I go to day 25, here we discussed what is the Kubernetes core and what are the extensions that are used to extend the capabilities of the Kubernetes core. Kubernetes core is essentially your control plane components and the node components. So the community, the Kubernetes community, actively works on development of items that are part of the control plane and the node components. However, anything else, the list that you see here is just indicative. There are many more plugins, add-ons, and third-party extensions that are used to enhance the capability of your Kubernetes cluster. For example, the Kubernetes core says, I have defined certain interfaces as in CNI, CSI, and CRI, where I define this is how networking, storage, and container runtime should look like. As long as you adhere to the standards that are defined in these interfaces, you can have your own networking, own storage, and own container runtime. Hence, there are multiple organizations who have come up with CNIs, CSIs, and CRIs. And similarly, there are different add-ons that can be integrated into Kubernetes cluster. There are third-party extensions as well, as you see here. What happens is Kubernetes community is the one who will set the standards for CNI, CSI, and CRI, and then Kubernetes community is governed by CNCF. Hence, we say that Kubernetes is a CNCF project. And it is not just Kubernetes that is part of the CNCF project. There are many more projects under CNCF like Prometheus, Istio, Envoy, etcd, Helm, CodeDNS, and there are many more. And most of these tools you will be learning as you progress with your DevOps journey. But why are we discussing this now? We are discussing this now because historically storage was integrated into the Kubernetes core itself. There was no concept of CSI, and at that point of time entry drivers were prevalent. There was a problem with entry driver. Understand that if you have integrated storage right in the core of Kubernetes, and we know that there are various storage vendors, there is NetApp, there is Dell EMC, and then you have cloud storage options. It is not possible for Kubernetes to take care of everything. And even if, let's say, AWS writes their own entry drivers, it still must be integrated into Kubernetes core. And if you integrate that, for everyone to use those drivers, there must be a Kubernetes upgrade so that you can use those drivers. Hence, whenever there was a new storage vendor, or there were new features, or we had to remove certain bugs from the existing entry drivers, then it was a mandate that the entire Kubernetes version must be upgraded. Now, this is not an efficient way to do things. We want developers and storage vendors to work independent of the Kubernetes core. If they introduce a new feature, then I just want that feature to be upgraded. And if I want that feature to be upgraded only, then CSI is the way to go. If I'm using a previous version of CSI, I introduce a new version which has all the new features. For example, Amazon releases a new version of CSI driver. That driver has a volume expansion. Now, to have that feature, what I will do is I'll just upgrade the CSI driver and I can use the volume expansion feature. Now, entry drivers, you would still see them used, but all the modern implementations of Kubernetes will have CSI. Now, if you as an administrator have an option whether to use entry or CSI, then you should pretty much always choose CSI, because the development of CSI is done actively by the storage vendors and the community that takes care of that particular CSI driver. Now, before I move to the next section, I quickly want to show you what are the examples of entry drivers, and we'll also look at documentation where we clearly see that these are now deprecated. So examples are AWS EBS, Google Persistent Disk. But Varun, these are modern things which are available in cloud providers now. Why are they deprecated? I want you to understand that we are not saying that these storage systems are deprecated. We are just saying the way these storage systems were accessed has changed from entry to CSI. Entry was something that was embedded into the Kubernetes core, and it defined if you are using entry, then if you are mounting an EBS volume using entry drivers, then that part is now deprecated. So if I go to the Kubernetes documentation and I search for volumes here, I go to volumes, and if you look at the index on the right, you see Elastic Block Store deprecated, Cephs deprecated. So these are now deprecated. The latest and greatest is CSI. Now, what is CSI? Like we discussed, CSI is a standard that is set by Kubernetes community. Anyone who adheres to that standard can write their own plugin, and that plugin can be used by Kubernetes to access the respective storage system. Check the provisioner field in the storage class to confirm. Now, how do I know whether I am using entry drivers or CSI backed? We have not discussed these terms yet. What is capacity, access mode, storage class? We have not discussed these. But I want you to know this, that you can always check whether you are using in-tree or CSI backed. In in-tree, you would always see the name directly here, AWS Elastic Block Store, and in CSI backed, you will always see something like CSI, and then you will see the provisioner as well. Here the provisioner is ebs.csi.aws.com. so that's the differentiator for you. CSI backed are available for both file and block storage. Now, what is file and block storage? File storage is something that you will be mounting onto multiple Linux system. For example, if you have 10 applications and all those 10 applications want to access a common file share, then you would be using file storage to allow multiple systems to access the same share, and they could be reading data from it and they could also be writing data onto it. What is block storage? Block storage is typically accessed by a single system. For example, if you have a laptop and you attach a USB drive to it, it is only your laptop who can access that USB drive. It's private to your laptop. Similarly, block storage is typically used by a single system, and I'm using the words typically and usually because there are always corner cases where there would be a file share that is only accessed by a single system and a block storage that is accessed by multiple systems. But in typical use cases, file shares will be accessed by multiple systems. You will be using file share when you want to give multiple systems access to a shared storage. You will use block storage when you want to attach a separate storage to your pod or to your laptops. Now, examples of block storage could be your databases, transactional system, and file storage could be any shared workloads. Maybe your web servers want to access a common share. So use cases like this would be using file storage. Now, there are CSI drivers available for both file and block storage. And whenever I'm saying CSI driver, do not limit yourself to think that these are only available on cloud providers, not on premises. There are multiple CSI drivers that are available for both on premises and for cloud deployments. And they are not only available for file storage or block storage, they are available for both. For example, if you are working on Amazon, there is a CSI driver that you can use to access the file storage on AWS, which is Amazon EFS or Amazon FSx. And you also have CSI drivers that can be used to access the block storage from Amazon, which is Amazon EBS. If you see the examples here, AWS EBS CSI driver, GCP persistent disk CSI driver, vSAN CSI driver. If you are into Broadcom's ecosystem, then you can use this on premises. Then there is Portworx CSI drivers. You could be using this when you are using an on-premises storage. And there are different storage vendors like NetApp, Dell EMC. They will have their own CSI drivers for both file and block storage. Then Varun, what about object storage? How do I access my object storage from my pods? Do we have CSI drivers for that as well? So what is object storage? Object storage has a flat architecture and you can access the files using URLs or REST. Then how do I access object storage? Firstly, object storage is not supposed to be mounted onto your pods. If I talk about file and block storage, this can be mounted, but object storage is not mounted. What you can do is your pod can make API calls to access the object storage, or your application could be using SDKs that are available from different vendors to access their object storage. So if you want to access Amazon S3, then you would have an SDK and you will configure that SDK along with your application, which will help you access that object storage. The command that you can use to check your CSI drivers is kubectl get CSI drivers, or you can look at the storage class, which is SC, or PV, which is persistent volume. Both SC and PV we have not discussed yet, but if you run kubectl get PV and the name of the PV, then you can know which CSI drivers you are using and also confirm whether you are using CSI drivers to begin with or not. If I have to summarize this section, I would say that earlier Kubernetes supported a lot of built-in drivers called entry plugins, but today the ecosystem has fully moved to CSI drivers, which are a future-proof way to provision and consume persistent storage in Kubernetes. So whatever storage you are dealing with, AWS EBS, NFS, iSCSI, Fiber Channel, if you are doing it the modern way, you are doing it with a CSI driver. Let's now move to the next section, which is hostPath. Now hostPath is a type of persistent storage, and hostPath is a special use case. Why is it a special use case? It's a special use case because hostPath uses entry drivers and there are no CSI drivers available for hostPath. hostPath is not a recommended way to create volumes in Kubernetes. Kubernetes does not recommend it. Why it does not recommend? Because hostPath uses the underlying storage of your node, and when you use the underlying storage of your node, you are essentially creating a directory in your node and then sharing it with a pod. If that pod is malicious, it could do certain things in your directory which are not permitted. Hence, Kubernetes says it is a security concern if you use hostPath volumes in your production environments. Hence, you can use it for testing, and if you have tight controls, if you have only given the permissions that are needed, then they will not pose a risk. But you must understand that Kubernetes does not recommend using hostPath in production grade environments. Now the first line says mounts host node files or directories directly into the pod. So this is what we defined right now. If there is a directory in your node, you can directly share that with the containers in your pod. Similarly, if there are files, you can also map those files as volumes onto your containers. I have this diagram here, and I have put this here to explain you what exactly is the host nodes storage. Because if you are on cloud, let's say your worker node is running on an EC2 instance, then that EC2 instance storage will be called the nodes storage. So if you have a pod running on, let's say, that EC2 instance, then that pod can have files or directories mounted onto it using the hostPath volume. But we are using Docker desktop, hence it is an important distinction I want to make. When it comes to Docker Engine has an architectural caveat which only allows Docker Engine to be configured onto a machine that has the Linux kernel, and Mac OS and Windows do not have a Linux kernel. So what Docker has to offer is Docker desktop. So what we have done is we have installed Docker desktop, and when you install Docker desktop, a lightweight Linux VM is configured for you, and that lightweight Linux VM has the Docker engine installed. And we are using Kind to create Kubernetes cluster. Kind is Kubernetes in Docker. Hence, our Kubernetes cluster is essentially comprised of 3 nodes, and all those 3 nodes are running as containers. So the first one is control plane node, then we have 2 worker nodes. Any containers that run are running on worker node 1 or worker node 2. Control plane is running control plane components. When I create a pod on top of a worker node, then the underlying host storage for that pod is the storage offered by this worker 1, this container, and this container is indirectly using the storage from this lightweight Linux VM, and this lightweight Linux VM is using the storage from a Mac OS. The underlying storage is still Mac OS's storage, but the nuanced difference is worker 1 container is giving the storage to the pods that are residing on worker 1. If you have installed Docker engine directly onto this, let's say, an Ubuntu VM, then your Ubuntu VM's storage is called the host storage. That's a nuanced difference. In summary, if you are using Mac OS or Windows, the node storage is provided by this container, and if you are using Ubuntu, then the host storage is provided by this worker 1. Persists beyond the pod's lifetime as it maps to a path on the host node's file system. This is understood. If something is lying on your host node, then that will not be deleted when the pod is terminated. Enables data sharing between containers in a pod and across pods in the same node. This is an important distinction. When we were discussing MTDIR in our previous lecture, we said that all the containers part of the pod can access that MTDIR volume. But with hostPath, we are saying all the containers in the pod can access that volume, but also any pods that are residing on the same node as the node which has the host path volume can also access that. So understand it this way. Host path volume, if we are using this worker 1 for example, we have created the host path volume here. So any pods that are created on this worker 1 can access that host path volume. Then what are the use cases for host path? Use cases are, you can use this for scratch space. What is scratch space? Scratch space is a temporary storage that your pods can use. Then caching. The underlying storage with the host is usually pretty fast. If you want to use that for caching purpose, you can use it. Now, there are niche use cases where you may want your pods to access the host logs. So what you can do is, you can map the host logs directory onto your pod so that your pods can access host level logs. Again, I'll mention, if I go to the documentation of this and I check host path, then you would see using the host path volume type presents many security risks. If you can avoid using host path volume, you should. Let's go back to our diagram. And now let's go to Visual Studio Code and do a demo for host path. So I'll go here, day 27, and day 27 has already a skeleton YAML for a pod. I've not added any host path characteristics as of now. So let's add the fields associated with host path. So what I'll do is, I'll first create a volume, a host path volume, and understand I'm not doing anything separately. A host path or MTDIR is created within the pod manifest itself. You do not have to define them separately anywhere. So what I'll do is, I'll add a volumes section and then I'll name this volume host volume. Okay, then I will mention host path. And we learned yesterday that under the volume section, you type the type of volume that there is. Okay? We are creating a host path volume, which is why we are writing host path here. So I'll add a colon, press enter, indent it, and then I will write path. Now what I'm saying is, the name of the volume is host volume and the host path, as in the path in my host where this file or directory is this. I'm saying host file. Now what I'll do is, I'll press enter, type. This is an important part. Here I will write file or create. So what I'm saying is, if this file does not exist, then create this file. So in case my host system didn't have this file called host file, then this would have created. Now since we already have host file, for example, let's say if you had this host file, then you could have just written file here. So let's go to the documentation and look at what other types are available at your disposal. Yeah, so these are the types that are available: directory or create. It's simple that if the directory does not exist, it will create it. Directory, if you already have the directory, you can just use this. File or create we have just discussed, and file we have also discussed. There are few more types that you can see and use as appropriate. I'll go to Visual Studio Code. Now what I have done is, up till here I have introduced a volume to my pod. Okay, but what I have not done yet is, I have not mounted that volume onto a container. This is an important concept and this should stay with you. First you introduce a volume to a pod or multiple volumes to a pod, and then you have to map map those volumes onto containers. So this is a very good way to do things. So if you have a volume and let's say you have 3 containers, you can choose to only map that volume onto a single container if that is what your requirement is. So let's do one thing now. We have one container in this pod. Now let's map this volume onto this container. I'll simply write VolumeModes because here we are creating the volume and here we are mapping the volume, which is why you see here VolumeModes. And where do I want to mount this volume? What is the mount path where I want to mount this volume? The mount path for that is /data. Let's say here is the place where I want to map this volume or mount this volume. And what is the name? Here the name is, what is the name of the volume that I want to mount? I want to map the volume with name host volume. So I'll write here host volume. That's it. We are done. So let's do one thing. Let's save this file. Let's go to our terminal, and I am already in day 27. I will now write kubectl apply -f hostpath.yaml. So I have that created. If I run kubectl get pods, I will see that there is a host path example pod running. There are 2 more pods. These are from our previous lecture. So if I run kubectl get pods -ovide, I know that this pod is created on my second cluster worker 2. So the next pod that I will create for testing will be on this node. So I'll just copy this name so that I can use it later. And then what I will do is I'll run kubectl exec to go inside the pod or to run commands onto this pod. Then I'll write -it. -it is give me an integrated terminal because I want to go into the pod and then insert some data into that file it. And then what I'll do is I'll name the pod. I'll write the name of the pod, which is hostpath -example. Then I want to run bin sh. I want a shell. So I am inside the pod now. If I run ls, you see that there is /data. Since we are mapping a file, that file is mapped on the mount path /data. So if I go here, I can just do vi data because data is a file. So if you see here, we have mounted host file onto the path /data. Now if I vi data, I can insert here, this is my file, do not touch it. Again, it's fill, let me write file, and then I will save this. If I cat data, you see that this is my file, do not touch it. What I'll now do is I'll go in Visual Studio Code and I want to create one more pod. So I'll call this pod hostpath example2. Let's edit the same YAML. And here I will add one more property, and that property is node name. Node name is I want this pod to be manually scheduled onto this worker node. Then I will save this. I'll go back to my terminal. See, all the volumes and the mount path for this pod will also be same as of our previous pod. And ideally, since the data in the host path volume can be shared amongst all the pods that belong to the same node, we should be able to access this data. So let me go back to my terminal and let me apply this file. kubectl apply -f hostpath.yaml. It says that the pod is created. I'll run kubectl get pods and I see that the pod is in a running state. Now I will run kubectl exec. I won't add a -t this time because I will be running the command from this itself. I'll write hostpath example2 and then I will write cat the file data, and you see our data is available in here. And let's do one more thing. If I create another pod here, let me call this 3 and let me create this onto worker 1, and worker 1 is just called worker, I think. Yeah, it's just called worker. So I'm creating this in worker. Ideally this should not be able to see any data that is here. I will run kubectl apply -f hostpath.yaml, and let me also change the pod name is already changed. I'll press enter. it is created. If I run the same command and here I will write example3, then you see it is not able to display anything because that data is not here. As we mentioned, the pods can access the data as long as that pod resides onto the same node. So the previous two pods that we created resided on worker 2, which is why they were able to access the host path volume, and this pod is not able to access because we have created this in this worker. If you see kubectl get pods, this one was created, the third one was created in only this node, worker node, and our previous two pods were created in worker 2. I hope this is understood. I will now clear my screen. I will delete these pods, kubectl delete pods, host path example, host path example 2, host path example 3, downward API as well, I don't want that, example, and downward API volume. I'll also add a force here so that the pod object is deleted immediately. I'll press enter and all of them are deleted. I'll now go to my diagrams again to discuss the next topic, and this is a meatier topic. What are PV and PVC? Forget PV and PVC. Let's first discuss what is happening with the diagram. So we have a physical storage. Now this physical storage could be your SAN storage, and then this is your Kubernetes cluster. Your Kubernetes cluster has a pod, and that pod has two containers. We have a PV here and we have a PVC here. What is PV? PV is a logical abstraction of the physical volume. So what, Varun? If you talk about a Kubernetes cluster, like I told you, there must be a physical storage somewhere available, and then that physical storage is mounted onto your Kubernetes cluster. So if I talk about this diagram, there must be a physical storage that should be providing this 5 GB. Hence, PV is a logical representation of the storage that you need. And what is PVC? PVC is persistent volume claim, and persistent volume claim essentially claims a persistent volume. The relationship between PV and PVC is 1-to-1, which implies only one PVC can put a claim on a PV. Then what happens is, then you have a pod. A pod can call this PVC, and any storage that is available in this PV can be accessible to this pod. So once that pod has that volume, any containers part of the pod can map that volume. When you schedule a pod onto a node, then that pod uses the resources of that node. For example, if this pod requires 1 vCPU and 4 GB of memory, then this pod is taking those from this node. Similarly, when you have a PVC, PVC will use the actual physical resources available with the PV. For example, here we are creating a PVC that is requesting 2 GB of storage, and when you make that request, this PVC will be using 2 GB provided by this PV. Like this pod was using 1 vCPU and 4 GB provided by this node. I hope this clarifies the difference between PV and PVC. Now let's see the entire workflow, how it happens. I have deployed my application onto a pod, and that pod has 2 containers, and my application requires 5 GB of persistent storage. What the flow will be? I'll go to my Kubernetes administrator because I am the developer. I'll ask my Kubernetes administrator that I want a 5 GB volume. My Kubernetes administrator will coordinate with the storage admin, because storage admin is the one who is managing this physical storage, and storage admin will create a 5 GB volume. Since my Kubernetes cluster already has CSI plugin installed, my Kubernetes cluster can interact with this physical storage. Then Kubernetes administrator will create a PV of 5 GB. Then I'm saying Kubernetes admin or developer creates the PVC, because this can be an overlapping role. In most environments, I have seen Kubernetes admins taking care of everything from end to end, but there are scenarios when you would see developers are the ones who are creating the pods and PVCs for themselves. You as an admin will only have to take care of PV, and as we progress with the course, we'll see that the role of PV will also be automated using storage classes. Developer calls the PVC in the pod deployment manifest. So once the PVC is there, developer can call that PVC to have this 5 GB storage associated with the pod, and then developer has a choice. Developer can mount that volume onto both of these containers or onto a single container. That is the entire workflow of PV and PVCs. Now let's evolve this architecture further. If I move down, we have the same diagram. What I have done is the PVs are here. There are multiple PVs of different sizes, and then there is an application one namespace here. But why we are mentioning namespaces? So let me go to the terminal, and if I run kubectl API resources, it will tell me all the Kubernetes objects that are available at your disposal. If I scroll at the top, I see there is PersistentVolumeClaims, and then there is PersistentVolumes. You see here PersistentVolumes are not namespaced. If something is not namespaced, it implies that it is available to the entire cluster. For example, nodes are also, you see, namespaced is false because nodes are available for the entire cluster. Similarly, persistent volumes are available for the entire cluster. However, persistent volume claims are namespaced, and the pods are also namespaced, as we have seen in our previous lectures. So both pods and persistent volume claims are namespaced, but persistent volumes are not namespaced. Now, why does it matter? So let me go back to our diagram. If let's say there is a pod in application 1 namespace, and then that pod has requested for 5 GB of volume. Now I would have created a PVC, and in that PVC I would have defined that this PVC is part of app1 namespace, because if you create any resources and you want those resources to be part of a specific namespace, then under the metadata section you define the namespace. For example, if I would have wanted this pod to be part of a different namespace, I would have defined a namespace here. If pod has claimed this PVC and this PVC is bounded to, let's say, this PV, then understand that this PVC cannot be used by any pod that is not part of this namespace. If there are multiple pods in this namespace, they can access this 5 GB volume just fine. If your use case wants other pods to also access that volume, that is possible, but you cannot have application 2 namespace access this PVC. And remember what I told you in the previous section. I told you that there is a one-to-one relationship between PV and PVCs. If this PVC is consuming this PV, then any other PVC, even if it wants 5 GB, it cannot be bounded, it cannot be associated with this PV. Hence, there is one-to-one relationship. I hope this concept is understood. Let's move to the next section. So we have the same architecture. We have a physical storage, then we have a 5 GB PV, we have a PVC, we have a pod, and then we have a single container. The flow is pretty much the same like we discussed before. So first, let's say what happens. Developer requests for a 5 GB volume. I, as an administrator, create a persistent volume. So the persistent volume, the kind is persistent volume. The metadata, I'm naming this volume example PV. The capacity of this volume is 5 GB, and our storage admin would have given us 5 GB of storage. And then there is something called access mode. Access mode is read write once. What does access mode mean? Access mode essentially govern how the volume is mounted across nodes. So whenever I say access modes, I want you to think in terms of nodes, worker nodes, not pods. So let's go to the GitHub repository and let me scroll down, and here you see access modes. There are 4 types of access modes that you would often see being used. What are these access modes? When I say read write once, I want you to think from a node perspective. The volume can be mounted as read write by a single node. Read write once by a single node, and then once it is mounted onto a single node, then multiple pods can access that volume in the same node. So whenever you see once, think of block storage. Whenever you see many, think of file storage. So if your pod wants to access block storage, and block storage we know are typically used by databases and high transaction systems, then the access mode will use once. And why is that? Because like we talked before, block storage is supposed to be accessed by a single system, whereas file storage is supposed to be accessed by many systems. What is read write once pod? Read write once is similar to this, but only one pod can access that volume. And this was recently introduced in 1.29, and we are on 1.32. And then you have read only many and read write many. Read only many, the volume can be mounted as read only by multiple nodes simultaneously. If a volume is mapped to multiple nodes, then think multiple nodes can have multiple pods, and all those pods can be accessing that volume. Read write many. Similarly, here only read access was there, and here we are saying both read and write access. The volume can be mounted as read write by multiple nodes simultaneously. Just go through these because these are important concepts to grab. Access mode is read write once. Here we understand that this volume can be used by a pod that resides on a specific node, and then there could be multiple pods that are accessing that volume. Host path is path /mount/data. In actual production use cases, you would have the name of the actual storage here. So if I move above, here you see there was this actual name of the storage, and here we were using CSI, so actual name of that storage was there. But since I am on kind cluster, hence I am using a path that is shared from my local nodes storage itself. That is why I'm saying host path here. Then the next one is persistent volume claim. So once the persistent volume is created, you create a persistent volume claim. Persistent volume claim is an essential item, because if access mode I do not read write once, which is same as the persistent volume, then this persistent volume claim will not be able to bound with persistent volume, because the access mode should be same. Only then a PVC will be able to bound with a PV, and there are few more conditions which we will see later in this lecture. Then what resources I am requesting? I am requesting for 2 GB of storage, but this one is a 5 GB. I am requesting only 2 GB here. Even then the bound will happen, because when it comes to storage provided by PV should be equal to or more than demanded by a persistent volume claim. So here if I am saying 2 GB, but the volume I have in my cluster is of 5 GB, then also persistent volume claim will be able to bound with this persistent volume. And then I have a pod. If you see, pod is calling this volume here. Pod is saying the name of the volume is persistent storage, and the persistent volume claim I want to use is example PVC. You see the correlation? It is calling the PVC here, and once the PVC is called in the volume section, then I can mount it onto any of the containers part of this pod. And here you see the volume mount. The mount path is this, because this is where I want to mount this volume, and the name of the volume is persistent storage. is taking it from here. I hope this is understood. Let's see the next flow. Next flow is also similar. Now why I'm showing you these flows is I want you to understand the options that you have available here one by one. I do not want to bombard you with everything in a single place. Now in the next one, what we have done is we are using AWS cloud for storage, and then we have a Kubernetes cluster. Now this Kubernetes cluster could be onto EC2 instances, or this could also be Amazon EKS. Same thing, we have 5 GB volume PV here, a PVC pod with 10 GB volume. This should also be 10 GB, please pardon me. Yeah. First we create a persistent volume. This persistent volume says capacity is 10 GI, which is why you see a 10 GB volume is created. Then the volume mode is file system. What is volume mode? Volume mode is whenever Kubernetes present this volume to your container, it will format it into a file system. For example, here the file system type we have defined is ext4. So whenever this container will see this volume, it will already be formatted with ext4 file system. But the other option you have with volume mode is block. So when you use the volume mode as block, and do not confuse this block with block storage, okay? This is different. So whenever the volume mode is block, the volume that will be presented to the container will not have a file system, and that container will have an option to format it as per its liking. So some of the Oracle and Mongo databases would want a volume mode as block. This is again dependent on use case. So if you have used VMware products, you would have heard of raw device mappings, RDMs. So RDMs were similar to this. You wouldn't format RDM with VMFS file system, which was VMware's file system. You would present RDMs directly into the OS, and OS would format that as per its liking. Similarly, you have volume mode block, which can be used if you want to provide the volume as a raw volume. Then access mode we have already discussed. Then there is persistent volume reclaim policy. Persistent volume reclaim policy defines what happens to the physical volume if the persistent volume claim is deleted. Should I be retaining it? Should I be deleting it? So let's look into different persistent volume reclaim policies, and these are often called reclaim policies. Let's just go here. I'll scroll down a little, and here you see reclaim policies. Reclaim policies, the first one is delete. Delete implies when this PVC is deleted, you also delete the corresponding persistent volume. Retain implies that when I delete the PVC, you retain the PV, and you would be using this when you want to audit the data and when you want to check the data. But when I talk about any cloud implementations of Kubernetes, you would often see that delete is being used, because when you delete the pod and the PVC, you also want the PV to get deleted, because in cloud you are paying cost as you use, and EBS volume has a cost associated with it. Common for dynamically provisioned storage, which is often you would use dynamically provisioned storage when you are on a cloud provider, and we'll see what dynamically provisioned storage is in a later section. There is also recycle, which is now deprecated. Recycle would essentially run rm-rf in your volume and delete all the data. Now there are modern methods available like retain and delete, hence recycle is no longer available, because recycle was also removing all the data manually. Instead of this, you can delete the volume and then recreate it. Let's go back to our diagrams now. Then we see a storage class name. Storage class we'll discuss in a little while. Then you see CSI. This is the part we all love. We want our storage systems to be accessed using a CSI driver. Here I am using an EBS CSI driver. I am saying the volume that this PV is associated with, its ID is this, and this is a volume that would actually exists in your AWS cloud with the ID as mentioned here. And then we are saying that the file system type is ext4. Now if I want a persistent volume claim to be associated with this persistent volume, then I would want to have these characteristics defined in my PVC as well. So for example, access mode read write once, I have read write once here as well. Here I am requesting 10 GB of storage, and this PV has 10 GB of storage. Volume mode is file system, and volume mode must match. Access mode must match for the bound to happen. If you see, volume mode is file system, and here also the volume mode is file system. Volume name EBS CSI PV, and here is the volume name EBS CSI PV. I am asking this persistent volume claim to only look for volume whose name is this. If this would have not existed, then the PVC would remain in pending state. Then storage class name, when you see just double quotes mentioned here, that implies that do not use any storage class. Now here I am saying the persistent volume claim that you should be using is EBS CSI PVC, and EBS CSI PVC is here. And then once I've added the volume to the pod, I'm calling that volume, I'm mapping that volume onto a container, and you see here the name is EBS storage, and EBS storage is the name of the volume that I defined here. Hence I'm mounting this volume here. Now let's do a demo for this. So let's go to the terminal. I'll clear my screen, and if I go here, I run kubectl get sc. Sc is storage class. Now if you have been following along with this course, you would also see that your cluster has a storage class. Even if you are Minikube, just run this command, because before I continue with this demo, I want to delete this storage class, and we'll recreate this storage class once we discuss storage classes in a little while. So let's do one thing. I'll take a backup of this storage class first, because we'll have to create it later. I'll run kubectl get storage class. Sc is the short name for storage class. I'll write -o YAML so that it gives me the output of this in YAML format, and then I want to redirect this output onto a file called sc.yaml. I'll press enter, and if I cat this file, then you would see that I have a backup of my storage class. What I'll now do is I'll run kubectl delete sc, and then the name of the sc is standard. It is deleted. If I now run kubectl get sc, I don't see a storage class here. I'll clear my screen now. Let's go to Visual Studio Code and look at the storage classes created here. You can see it, and then let's go to PV here. Here what I am saying is create a persistent volume for me, and the name of the persistent volume will be this. We have seen this exact YAML before, and I've just added a few more sections. Then you see the capacity is 5 GI, access mode is read write once, and then the reclaim policy is to retain. Like in hostPath, usually you would see that it is retain, because if let's say you delete the PVC and you recreate a PVC, you might want to give other pods access to the same data. Similarly, you would also see retain policy when it comes to file storages, because there are multiple pods which were accessing that file storage, and you might not want to delete that file system. Hence you would use retain. With block storage, be it on cloud or be it on premises, I have seen administrators using delete as their reclaim policy. So I have this reclaim policy of retain because this is sort of a file storage that is made available by my hostPath, since we are not using an actual SAN backend. So what I have done is I have used a hostPath, and the path is /mount/data. So this is our persistent volume. Then let's see the persistent volume claim. Hold on, why I am not able to? Yeah, I'll do is I'll right click on this and I'll split this to right, so that we can see both of these. Here we have a PV, and here we are creating a PVC. Now this PVC, again, you see that this is of 2 GI. Even then it will claim this because the PV should be providing storage equal to or more than the PVC. Access mode is read write once, which is same as this, and then there is a storage request of 2 GI. And then we also have a pod, and let me again split this to right so that you can see all all three together. I'll do this. Yeah, here we are creating a pod, and that pod has a volume, and that volume is referencing the PVC that we created here, example PVC, and the name is persistent storage. And if I go to the volume mount, I see the mount path is this, and the name of the volume that it is calling is persistent storage. Now let's go to the terminal and apply these YAMLs. So I will go here, I'll first apply the PV kubectl apply -f pv.yaml, and then I will run kubectl get PV. If I run this command, you see the status is available. So right now this PV is available. There is no claim associated with this. Storage class we have not defined. Reason is blank, and the age is 3 seconds, and the access mode is read write once. Capacity is 5 GI. We can also run describe and see if this provides any further information. Describe, and it is also providing the same information, but it is also providing us the source of this PV. Well, let's do one thing. Now let's also apply the PVC kubectl apply -f pvc.yaml. Now if I run kubectl get PVC example PVC, then I see status is bound. Why is the status bound? Because it would have bound with the PV that we created in the previous step. The capacity is 5 GI, the access mode is read write once, storage class is blank, and then age is 7 seconds. If I again run this command for the PV kubectl get PV, then you would see the previously the status was available, but now the status is bound. And did you notice one thing? In here the PVC we created was of 2 GI, right? But here you see that the capacity is 5 GI. And why this is 5 GI? This is 5 GI because the PV we created was of 5 GI capacity. Now if I do one thing, if I kubectl delete PVC delete -f pvc.yaml, and then also let's delete the PV, and then let's just create the PVC first. Kubectl apply -f pvc.yaml. If I press enter, if I now run kubectl get PVC, you would see that the status is pending and the capacity is not yet defined. If I create kubectl apply -f pv.yaml, and that is applied now. Now if I now check kubectl get PVC's output, it is still pending. Now it is bound since we have created the persistent volume. I'll also run a describe on kubectl describe PVC example PVC, and you can see that failed binding. This was 31 seconds ago. At that point of time the PV didn't exist, but now that it exists the status should be okay, because if I run kubectl get PVC, I see all things are working as expected. You should always see the status bound. Status bound implies there is a healthy PV associated with this PVC. If I run kubectl get PV, you see that all status is also bound here. So bound is what we want to see. Let's apply the pod YAML. Kubectl apply -f pod.yaml. If I run kubectl describe pod example pod, then if I scroll, if you see the mounts here, I see that this mount is from persistent storage. I hope you are able to connect the dots. You create a PV, then that PV is associated with the PVC, then that PVC is called in the volumes section of your pod, and then you map that volume onto any of the containers where you want to mount it. It is as simple. Just understand the foundational concepts, and be it persistent storage or ephemeral storage, it follows the same thing. So I'll clear my screen now. I will kubectl delete PV example PV. I'll delete my PV. It says the PV is deleted, but is it? My CLI is stuck here. So let me go here into, let me open another terminal and I'll zoom in here as well. Now let me run kubectl get PV. It says that the status is terminating. it is not terminated yet. The status is still terminating. Let me run kubectl get PVC. It says that the status of PVC is also bound, so the PV is not yet deleted. So let me run kubectl delete PVC example PVC. It says deleted. So let me open another terminal. So let me write again kubectl get PV, kubectl get PVC, terminating, but none has terminated. If I run kubectl describe pods example pod, then you would see it still has the mount. The point is, if a pod is using a PVC, then you cannot delete that PVC or the PV. So there must be a sequence. So if I go back to my diagrams, you first have to delete the pod if the PVC is being used, then you delete the PVC, after that you delete the PV. It's a protection mechanism by Kubernetes. You cannot delete a PVC if it is being used by a pod. Similarly, you cannot delete a PV if it is being used by a PVC. So if I go here to my terminal, if I run a command now kubectl delete pods example pod, I press enter, now you see everything would have started working. If I go to this tab, it says deleted. If I go to this tab, PVC is also deleted and PV is also deleted. Kubectl get PV, I don't see anything. Kubectl get PVC, I don't see anything. I hope this concept is also clear. Now let's move on to storage classes. See, I had a problem with the previous architecture. Every time someone wanted storage, I was disturbed and I was not liking that. As a Kubernetes administrator, I want my life to be automated. I do not want to go and create PVs all day long, because the storage requests will continue to grow as your cluster and as your applications that run onto that cluster grow. The demand for PV will also increase. So I want a process in place which will ensure that whenever there is a request for storage, whenever someone creates a PVC, a PV must be automatically created. So I, as an administrator, or if let's say your developers are taking care of creating pod manifests and deploying applications onto your Kubernetes cluster, and you are just plain Kubernetes administrator. I'm saying this because now there is, with Kubernetes getting so popular, there are developers who are doing CKA and they also know how to deploy an application onto Kubernetes. So the infrastructure part, your CKA certification resources will be taken care of. Administrators who take care of administration of the infrastructure and Kubernetes, and then there will be developers who will be deploying their application. So at times we do not want developers to trouble administrators when they want to deploy their applications, and their applications could be using PV and PVCs. So as and when the developer creates a PV, storage is automatically provisioned for them. A corresponding PV is automatically created. That is what is called dynamic provisioning. So if I move a little down, then what is storage class? Storage class in Kubernetes is a way to define different storage configurations, enabling dynamic provisioning of persistent volumes. Persistent volumes is the key here. So if you look at this, you are not defining access mode in the storage class. What happens is, whatever access mode is defined in the PVC, that access mode is set for the PV as well. So what we are doing in this example, we have introduced two storage classes to the cluster. Varun, why we are doing this? If I talk about my Kubernetes cluster, my application could be using file storage, they could be using block storage, and in block storage as well, there could be categories. One could be a storage that provides lower IOPS, one could be block storage that provides higher IOPS. Similarly, there could be a file storage that is limited to a single availability zone when I talk about cloud, and then there could be a file storage that spans across different availability zones within a region. So there are different tiers of storage, a gold tier, a platinum tier, and you can do this tiering based on your requirement. Maybe application 1 needs SSD disks and application 2 just requires HDD, then you have an option to have multiple storage classes associated with your Kubernetes cluster. In the example you see here, we have GP3 type, and then we also have IO1. Both of these are coming from the CSI drivers, but their types are different. EBS is the volume type, and within that volume, the type of volume that we are creating, one is GP3 and there is provisioned IOPS, which is IO1. So let's discuss this storage class. Reclaim policy, like we discussed, you would often see delete reclaim policy when we are talking about block storage, and EBS is a block storage solution from Amazon. Type is here in this storage class, type is GP3, and here the type is IO1. IO1 provides you even higher IOP. Then we have created a persistent volume claim. This persistent volume claim says that create a PV for me whose access mode is read write once, and the storage I want is 10 GI, and the storage class I want to use is this one, EBS SC GP3, EBS SC GP3. So if I would have provided here EBS SC IO1, then this persistent volume would have used this storage class to create the corresponding persistent volume. Are you getting this point? Very crucial. You could have multiple storage classes, and in your persistent volume claim, you only call the storage class that you want to use. In this example, I wanted to use GP3, hence I called the class which is hosting GP3, and Kubernetes behind the scene creates a persistent volume that matches this PV. The burden of creating persistent volume is now gone, and here you see the corresponding persistent volume. The access mode is that, the reclaim policy is that, the storage class name is again populated from what you gave in the persistent volume claim. Rest of the things are picked up from your storage class. That's the magic that storage class provides. You see that file system is ext4. There could be certain defaults each storage class has to offer. For that, you will have to read the documentation to understand what are the defaults. Then here I have created a pod, and that pod under the volumes section, it is calling EBS CSI PVC, and EBS CSI PVC is what I created here. And then we have named this volume EBS storage. In the volume mounts section of the containers, we see that we are mounting this volume onto this path, and the name of the volume that we are mounting is EBS-storage. As simple as that. This is storage class for you, an important concept which will be always used in production grade implementations of Kubernetes. There is one thing I did not discuss, which is volume binding mode. Wait for first consumer. This says only create the PV once the pod that wants to use that PVC is created. What does that mean? It means that do not allow administrators or developers to just create PVCs. If they have just created PVCs, do not create an associated PV. Why? Because that PVC is not being used right now. Until and unless this pod is created, you do not create this PV. But Varun, what does it do? It saves me costs to begin with. If this pod is not created, then why would I want to provision a 10 GB EBS volume in my cloud provider? My cloud provider will charge me for 10 GB of volume. I don't want that. I only want to provision persistent volumes when there is a pod using that volume. Now, this is one use case why you want to use wait for first consumer. The other option you have is called immediate. So it will provision the persistent volume as soon as PVC is created. But I personally always use wait for first consumer. First is the cost benefit. Second is, let me explain that to you in this slide. What you have here is an AWS cloud. And that AWS cloud, we are using the Mumbai region, and in Mumbai region we are using 2 availability zones to deploy our Kubernetes cluster. Before I move forward, nodes and EBS storage are AZ specific. What I mean is, if I create an EC2 instance, that instance will either belong to AZ1 or AZ2. It cannot spread across availability zones. If anyone is new to the concept of availability zones, availability zone can be thought of as a single or multiple data centers which form an availability zone. In AWS, all regions will have 3 or more availability zones. For example, we are in Mumbai region right now. In that Mumbai region, we are using 2 availability zones. So nodes and storage are AZ specific resources. Now let's say if you created a PVC and a storage was created in AZ1 for you, but when the pod was scheduled in AZ2. How can pod in AZ2 access storage in AZ1? That is not possible. Hence, it is always recommended to use wait for first consumer, because when you do that, the PV is only provisioned once the pod that wants to use that is scheduled. And if the pod is scheduled in AZ2, then automatically the corresponding PV will be created in AZ2, which will make the bound happen immediately. Important concept, a nuanced concept. So let's go to our terminal and do a demo for storage class. I'll go to my terminal, and I also want to show you the contents of the file that we just backed up. I'll just close this, expand this, go to sc.yaml. If you see sc.yaml, the important thing to know here is these things. Our provisioner is rancher.io/local path. So this is essentially what is helping us do dynamic provisioning. And I want you to know one more thing. Whenever you are using storage classes in production, it is always that you would be using a CSI plugin for that. So if you see here, I'm using a CSI plugin, and with this CSI plugin, I would pretty much always use a storage class. So let's again go back to Visual Studio Code, and this is our storage class YAML. So let me go to our terminal, and here I will apply this storage class kubectl apply -f sc.yaml. I'll press enter. It says that the storage class is created. If I run kubectl get sc, I see that storage class is created. Now let's do one thing. I'll write kubectl apply -f PVC. I'm using the same PVC like we used in our previous example. I'll press enter. This will just create the PVC. I'll now run kubectl get PVC. It shows me that the PVC is in pending state. Why is it in pending state? Because the corresponding PV is not yet created. Why it is not yet created? Because my volume binding mode is wait for first consumer, and I have not created a pod that would be using this PVC. So if I run kubectl get PV, you see that the PV is not yet created. But as soon as I create a pod that will be using this PVC, I'll see that the PV is created. I'll run kubectl apply -f PVC pod.yaml. I'll press enter. I see the pod is created. If I now run kubectl get PV, voila! A PV was automatically created for you. If I zoom out a little so that this comes in one line, then you see that PV was created, whose name is this PVC-this, capacity is 2GI. Previously 5GI was used because we were provisioning that manually. If you see that PV, it was of 5GI, but since we are using an efficient process now, our PV will only be created based on the size of the PVC. Our PVC just requested 2GI. Hence, we provisioned a PV that was of 2GI capacity, and you see the status is bound. The storage class we are using is the standard one. Now let me run kubectl get PVC. That status is also bound now. I'll just zoom in a little, and I'll run kubectl get pods, and my pod is also running. If I run kubectl describe pods example pod, then I would see that there is a volume that is mounted from persistent storage. I hope all the dots are now connected and you understand what is happening. Now, before I let you go, I want to discuss one more thing. I'll go to my GitHub repository, and if I scroll down, I would want you to read these things PV and PV binding conditions. I have written the conditions that should be met for a PVC to have a claim on PV, and for that bound message to happen. And then here is a summary chart as well, that the storage class must match. And we also understand these things. If you are mentioning a storage class EBS SC my storage, then you don't have a storage class with that name. So hence there must be a storage class with the same name. Only then a PV will be created. And then there are other things that should also match. Access mode should match, and we have seen that. So access mode read write many, then the PV must have read write many. So sufficient capacity must be available. Bounding volume binding mode we discussed, immediate and wait for first consumer. Volume state PV must be available. Matching volume mode we discussed about file system or block, so they also must match. I think that's all I wanted to discuss. I would request you to go through these GitHub notes because these cover everything that we have discussed. That concludes our deep dive into persistent storage in Kubernetes. We understood PV, PVCs and storage classes. You would be using these things all the time in production implementations. In the next lecture, that is day 28, we'll explore config maps and secrets. If you have any questions, feel free to ask me in the comment section and I will reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.